Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 55, and this is lecture number 9 of the Physical Chemistry chapter Solid State. The subtopic of this lecture number 9 for the last 5 lectures had been discussed was close packing in metals and metal compounds, and in the sixth part of this lecture the crystal structure of beta-Cristobalite is going to be discussed. Beta-Cristobalite is a high-temperature polymorph of silicon dioxide or silica, which has chemical formula SiO2. It has a cubic structure which is characterized by a three-dimensional network of corner-sharing SiO4 tetrahedra. Look here, this overall unit cell is made up of silicon atoms, and these silicons are arranged in face-centered cubic manner, that is, cubic close-packed manner. But apart from that, it has four more silicon atoms which are occupying each alternate tetrahedral holes. That means if we divide this unit cell into equal sized eight small cubelets, then each cubelet, each the body center of each small cubelet is equivalent to a tetrahedral hole. Now these tetrahedral holes are alternately occupied by silicon atoms. So since there are eight tetrahedral holes or small cubelets, therefore if the silicon atom is occupying it alternately, then there should have been four tetrahedral holes which are occupied by silicon atoms. Let us have a look on this picture. This is a small cubelet, or this is a tetrahedral hole by these four silicon atoms. Now, in the body center of this small cubelet, there is yet another silicon. Now, this type of small cubelets, total number of cubelets are 8. Out of this 8, 4 are occupied alternately. So, how many number of silicon you can find here? Here, 4 silicon in the unit cell, which is constructed in the unit cell, and 4 more silicon, which are inside the unit cell. Now, the hybridization in silicon atom is sp3, and that of oxygen is amazingly sp, not sp3. So, what about the type of bonding? This bonding is actually sigma bond, purely sigma bond between silicon and oxygen. And this sigma bond is sp3 type of sigma bond. Look, the silicon oxygen bonds are purely of sp3 type of sigma bond. Now, since this is sp hybridized, so there is the pure unhybridized electrons 2p and 2pz, and they should remain as lone pairs, or there is a probability of forming p-pi d-pi bonds with silicon. But the 3d vacant 3d orbitals are so much diffused that this probability has been rejected. As a result, the four non-bonding electrons on oxygen remain as lone pairs. But this is not, the case is not as simple as it looks. These electrons cannot be described. Look, the non-bonding electrons of oxygen within the crystal lattice, the 2p 2pz electrons cannot be classically described as the lone pairs. Okay, these electrons cannot be described as lone pairs. They are better described as extended wave functions or bands. This is something different thing rather than the classical concept which you have. So there is no probability of p-pi d-pi bond formation nor any probability of lone pair. There is a high electron density, and which can be only explained by extended wave function or the bands. So oxygen is sp hybridized and silicon is sp3 hybridized. Silicon is forming tetrahedral. That means silicon is surrounded by 4 oxygen. On the other hand, one oxygen is surrounded by 2 silicons. That is, it is bonded to 2 silicons, and simply silicon is bonded to 4 oxygens. And here you can see that in between two oxygen is bridging between these two silicons. Okay, so each silicon atom is bonded to 4 oxygen atoms in a tetrahedral geometry. On the other hand, each oxygen atom is covalently bonded to 2 silicon atoms linearly. As a result, the coordination arrangement of silicon is to oxygen has been found to be 4:2. The silicon oxygen silicon bond angle, that is this bond, silicon oxygen silicon, this is found to be 180 degree. This is, since this is sp hybridized, so this bond angle is 180 degree. On the other hand, this silicon is sp3 hybridized, so this bond angle should be like methane, that is 109.5 degree. Oxygen silicon oxygen bond. Silicon is forming the face-centered cubic lattice with 4 more silicon atoms in each alternate body center of the 1/8 size cubelet. That means if you divide this unit cell into equal sized small cubelets, 8 cubelets, then in each alternate cubelet, one more silicon is still occupying. So out of 8, there should be 4 more silicon atoms. There is total, therefore, 8 silicon atoms. So how 8? Since these silicon atoms are forming the body center, face-centered cubic lattice, so 4 are inside and 4 more are there. So 4 plus 4, 8 silicon atoms. And how many oxygens? All these oxygens are inside. Okay, this silicon in the tetrahedral hole are bonded to 4 oxygen. So this way, this silicon is bonded to 4, this is bonded to 4, and this one also bonded to 4 oxygen. So 4 into 4, 16 number of oxygen atoms are within the unit cell. So what should be the formula unit which is inside the unit cell? Actually, there are 8 silicons and 16 oxygens, so it should be Si8O16. If the stoichiometry is SiO2, then there is total 8 number of formula units which are inside the unit cell of beta-Cristobalite structure. So this type of structure is adopted by these compounds: aluminium phosphate, beryllium fluoride, boron phosphate, boron arsenate, etc. So that's all about the structure of beta-Cristobalite. Thank you. Have a nice day.